Hello. Today we're going to be talking about deriving the divider law, specifically the voltage and the current divider law. We will discuss what those mean later, but for now, let's go back to the three fundamentals, laws of physics. So first is the law of conservation of charges and energy. Very simple. If a system is a closed system, that means no charges or energy can enter or exit out of that system. Therefore, within that system, energy and charges remain constant. And of course, we have Ohm's law, which just states that voltage is equals to the current times the resistance of a system. So, how are we going to derive the divider laws? For one, the law of conservation of charges gives birth to Kirchhoff's current law, which states that the current going in and the current going out must be equal to each other, or the sum of all currents going in is equals to the sum of all currents going out. Again, current is just the amount of charges per unit time. And if the charges in a closed system is constant, this must be constant, or at least the sum of all Qs. And then per T is just a unit time. So this may be 1 second or 2 second or whatever. So the amount of charges must be constant, therefore the amount of current must be constant in entering and exiting. So that's one of the important laws of electrostatics. The next one is the law of conservation of energy, which leads to Kirchhoff's voltage law, which states that in a circuit like this, specifically a resistive circuit, you have a voltage source and you have something that causes voltage drop. The sum of all voltage source plus the sum of all voltage drops. This is what we call the algebraic sum. And the algebraic sum is essentially taking the signs into account. This should be equal to zero. So what do we mean by voltage source and voltage drops? Voltage source come from voltage sources, of course, like a battery or a capacitor, something like that. But although a capacitor is far more complicated than a battery. So for example, this is a 9-volt battery. The positive is here, the negative is here. Current goes that way, and it goes that way. Since the positive is in this one, uh, this must be the positive end of the resistor, and this must be the negative end of the resistor. Now, a resistor is actually not polarized, so it doesn't have a positive or negative side. Although the positive and negative sides in a circuit depends on where the voltage source is. So the positive and the positive must be in the same side within the battery, and the negative end must be in the same side of the battery and the resistor. Mm. So if you're going in a loop here, and let's say that going from negative to positive is a positive voltage, so this means going through the battery is 9 volts, so positive 9 volts. And since going to the resistor, we have to go to the positive towards the negative, which is in our convention, a negative voltage. This must be minus 9 volts. And this obeys Kirchhoff's voltage law. Doesn't matter what resistance this is, it still has 9-volt voltage drop. All right. What if, for example, you have like this 9 volts and then a resistor in between, and then another battery going in the other direction, maybe 100 volts. Noticeably, one of them is bigger than the other, but you won't really know the the direction of this. You just have to assume the direction. So maybe this is positive, negative, so it goes there. This is negative, positive, so it goes there. So we have to assume what direction this is. Most likely, it's going to follow the 100 volt, which is going that way. So this should be positive and negative. Again, this is an assumption of where the current is. Actually, the current must go that way. So the polarization of this resistor follows the polarization of the 100 volt source. And again, that's just an assumption. Maybe it goes the other way. But the calculation performs similarly here. For example, there's like a 100 volt. I don't know how many voltage. I don't know if this is even possible, but if you're going that way, for example, like that way, look at the look at the direction of current. This 9 volt goes from 9 volts to from negative to positive, therefore this is positive current. This is from negative to positive, therefore this is non-current. So whatever voltage drop this is VD. And of course, according to Kirchhoff's voltage law, this should be 0 volts. Now this doesn't look realistic, of course, but it's just a theoretical. So that's both Kirchhoff's current law and Kirchhoff's voltage law in a nutshell. And we've proceeded to learn why voltage drops exist right here because of the polarization and the direction of current. Again, we assume the direction of current. This is usually historical assumption. The current goes from negative to positive. So that's why. So now we should talk about how all of this works in a series circuit. So hold on. Let's draw a sample series circuit, a very simple series circuit with only one resistor. Let's say this is 9 volts, this is 1 kilo to keep the current low. Okay, so this is a loop, and Kirchhoff's voltage law works on loops like this and this and this. That's because KVL works in series like this one, so it should work on this. Why is the algebraic sum 0? Well, because the potential difference between this is 9 volts. So the potential difference, that really means that in here, this is a region of high potential. Let's say 9-volt potential. And in here, this is a region of 0-volt potential or low potential. Essentially, it's like a ball rolling along a hill. On top, there is a lot of potential energy. On the bottom, there is no potential energy since there is uh there is no a height to be expended anymore. So, for example, this is like 9 joules of potential energy. This is 0 joules of potential energy. The potential difference is the difference between the joules here and here. But instead here it's volts. And voltage is just the electric potential of a system. So what this really means is if you if you put a multimeter in here, it will show 9 volts. Sorry for the vertical multimeter, but it will show 9 volts. So what does that mean? Yeah, it means this 9-volt potential and 0-volt potential in these regions. Now, what does that actually mean? Well, if this is a source of 9 volts and there's 9 volts in this direction, this means that there is 0 volts in here, which from 9 volts here, there is 0 volts here. This means that the 1 kilo ohm resistor has a voltage drop of negative 9 volts, or the voltage dropped 9 volts within the resistor. Therefore, this region is 0 volts, 0-volt potential. The reality of this is more complicated, but that's how we like to think about it. The 0-volt potential, the region of 0-volt potential, we can actually call this ground. So the voltage of ground or VG is usually 0, and this is VS, which is usually the full volts, 9 volts. So, so from here, how do we what do we conclude from here? Well, that's what Kirchhoff's voltage law tells us. What about Kirchhoff's current law? So, for example, another circuit here, same parameters. The only junctions that exist in this is essentially this, right? Current goes in and current goes out. There's no triple in here, so an additional current goes out or in. So this is just going in and going out. This means that the current going in must be equal to the current going out. So within the circuit, the current in a series circuit must be equal to itself. In a parallel circuit, it's more complicated because there are branches, but in the series circuit, there is no branches. So whatever the current of the entire circuit is, that's the current that passes through every resistor, every source, blah, blah, blah. So we can conclude that the current in series is all equal. So whatever current flows here, whatever current flows here, it's all equal to each other. So how can we use those facts? Well, imagine a circuit with X amount of resistors. I'm gonna draw three, but there's an X amount of resistors. According to Kirchhoff's voltage law, this should be a region of 0 volts and this should be a region of 9 volts in terms of the absolute potential. And the relative potential or the potential difference is 9 volts. So this means that these three resistors, they all sum up to negative 9 volts in order for the 9-volt source to be zero. So that means that voltage total plus voltage drop, the sum of all voltage drops is equal to zero. Put in another way, Vt equals negative the sum of V drops. All right. All right. Let's drop the sign here and let's make this negative since voltage drop is negative. Make it easier than that. Actually, no, let's not do that. Let's try doing this. So we know Vt is just the V source. So we're not going to do anything about that. This is the sum of all voltages. We can dissect this into two. This would be the current times resistance. X is the X amount of R. So it's the number of all the resistors are cycling through it. Now, since voltage drop is a negative quantity, this is a negative quantity, we can say this is positive since current is positive. Uh, Going from here to here, it's actually VD is negative the current of the entire thing times Rx. So we can do that like here. So we can say Vt is equal to the sum of It times Rx. Now, the cool thing about this is that Vt, we can also say this is I times R. The current I should be I total since all the currents are equal to each other and the resistance must be the total resistance of the entire circuit. We will put that as our EQ, equivalent resistance. This is equal to the sum of IT times RX. IT is constant in here since they're all the same. RX differs. So what we can conclude is that if we divide both sides by IT, we get R equivalent is equal RX, the sum of RX in series. So resistances in series is sum, or we add all of them up. So in conclusion or in summary, the relationship can be described as follows. In a series circuit, the voltage is additive, so it's a sum, as we discussed in here, and in the Kirchhoff's voltage law. And in the current in a series circuit is equal to all the currents in everything in the series circuit. And for the resistances, it's just equal to the sum. So it's going to be sum. This is going to be familiar to some of you who watched the my earlier videos, but that's going to be in a series circuit. How can we extrapolate this into the divider law? Well, the voltage divider law works only in a series circuit, and for this exact reason. Now, let's say there's a voltage here, Vx, let's say Vx, yeah. And maybe the all of these resistances have Rx, like R1 or R2 or whatever. And then there's Vs, V source. And V source equals the V total of all of this. And The voltage source must be equal to the voltage drops of all of this, but the negative of the voltage drops in terms of the algebraic sum. So this means that Vt is equals to the sum of all V x's, Vx. There's also V like V1 and V2 here, and this is Vx, all the sum of Vx. Okay, so the current is the same throughout all of them, so we can divide. Oh, wait, hold on. Mm, so Vt is the sum of Vx. Sorry, I erased that, but that's true. So how do we find a singular voltage x, Vx? We know V equals IR, voltage equals current times resistance. This is Ohm's law. So we just need to find the current flowing through all of this, and we have the resistance X. So IT times RX. What is IT? This is going to be VX. VX equals IT RX. What is IT? Well, we can find the current using voltage source over the R equivalent. And in a series circuit, it's the sum. So V source or V total at this point over the sum of R times all of them. Let's say about what letter do you want? A, R A, I don't know. Uh let's just say RS for our sum, something like that. So we know that this is the current. We need to multiply by the resistance Rx. So in order to get Vx, we need to get the IT, which is this. This is IT. So it's going to be Vt over some Rs multiplied by Rx, or Vx equals Vt times Rx over sum of Rs. This is the voltage divider law. And this is useful for if you have like a lot of resistors, maybe in a series circuit, and you know the total voltage in this circuit, and you know all the resistances. You just want to find this particular voltage. You can use this one. So let me reiterate what this represents. This is the voltage in a particular resistor. Vt is the total voltage. Rx is the resistance, and some Rs is the total resistance. So that's going to be nice. All right, that's the voltage divider law. What about the current divider law? Well, the current divider law only works in parallel because in series it's all equal again. In a series circuit, VAR is SES. Sum equals sum. So current in series is equal. What about in parallel? Okay. So let's draw a parallel circuit right here. All right. This is a parallel circuit with a voltage source and three parallel resistors, but obviously there could be as many as like 100 resistors. I don't care. Uh, in here, how do we find the voltage drops of each? Look here. This is a loop. This is also a loop. This is also a loop. All of them are loops independent of the other resistors. So the voltage drop here, the voltage drop here, the voltage drop here must be equal to the voltage drop on voltage on the source, which is V total. So this means that voltages in parallel are equal to each other. What about current? All right. So this may be a little tricky to visualize, but let's redraw it. So you could redraw a parallel circuit like this. So like that. It doesn't sound truthful, but it's equivalent. There's nothing in here, here, or here. So there's nothing blocking it. So it could look like this. So this is a junction. These three are also junction. These two, this is not a junction. These two are also junctions. We can collapse it into one junction in here if it's truly parallel. So current going in, this is all current going out. By Kirchhoff's current law, all current going in is equal to all current going out. Therefore, current going in is just the total current, so ID. And current going out is equal to the sum of all current here, here, and here. So this means that since it is the sum of all currents, this means in parallel, currents are additive, or we need to add all the currents together in order to find the total current. Now, what about the resistance? Now, using these two definitions, we can say IT, sorry, equals to I1 plus I2 plus I3. Or let's make this more concrete. I1, I2, I3 are just the example. This is the currents here, but let's make it general. So the sum of IX. This is just what we learned later. This is due to the behavior of currents in parallel being the sum. So voltages is the voltage total will be VT over R equivalent. And then for the sum, again, voltages in parallel are equal to each other, so there's no need to change it. So it's just VT on top. And on the bottom, it should be each resistance of each resistor. So it should be Rx. Dividing VT on both sides, we get 1 over R equivalent equals sum of 1 over Rx. And if you want to simplify the formula further, you get R equivalent equals sum of Rx to the negative 1 on that this the negative 1. So that's going to be R equivalent. That's actually how we find the R equivalent in a calculator. It's like this. It's much easier to write. So in here, this is a special kind of addition, one we will call harmonic, since it involves fractions and addition of fractions reminds me of the harmonic sequence. So it's going to be H. So how do we derive the current divider law here? Well, we need to find in a series circuit, we need to find the current in one particular region or one particular resistor. So how do we find that? Mm-mm. First, we know that the currents are additive and the voltages are equal to each other. So whatever voltage goes on in here must be equal to the V total. So V total over Rx must be the current we are looking for. But what if we're given just the voltage or we're given just the current? How do we find the current? Hmm. For example, we're given the current I total, but we're not given VT or we're only given the resistances and the current. How do we how do we do like a divider law, like the voltage divider law? So IT is equals to VT over R equivalent, right? That is just Ohm's law. And we can rewrite R equivalent like that. So that's going to be VT over let me just X here so distinguish it, sorry. VT over the sum of Rx to the negative 1, then all that to the negative 1. All right. So in here we have VT. Here we have VT. Let's try to put VT in its place. How do we do that? Well, we multiply this thing on both sides to remove it. Just put it to the other side. So VT equals IT times mm, the sum of Rx to the negative 1 to the negative 1. And we now have Vt, therefore we can place this here. So Ix equals Vt, which is this, It times the sum of Rx to the negative 1 to the negative 1 over Rx. Now, this doesn't look clean. We need to remove this negative 1. This on the inside can work. Let's distinguish the Rx from the R. So let's just R here. Rs maybe. Let's just put R in there. So let's to distinguish this R. Yes. So let's put the Rx on the top, but make sure its exponent is negative. So Rx to the negative 1 over the sum of R to the negative 1. And this is the current divider law. Rx is the specific resistance you want to find the current of in a parallel circuit. This is the harmonic sum of a resistance, and this is the total current in a circuit. While this is the specific current that we want. So that is going to be the voltage divider law and the current divider law. I hope I explained correctly, and I will see you in a next video that bye.